All right, welcome to The Explainer. Today, we're going to cut right to the chase and tackle the core physics you absolutely need to know for your exam. We're talking Newton's laws.
So, physics exam tomorrow? Yeah, I get it. That pre-exam pressure is real. But don't worry, we're going to skip all the dense theory and focus only on what you need to actually solve those numerical problems.
Think of this as your super fast toolkit. The goal here is to give you a clear, step-by-step method that turns those confusing word problems into actual points on your exam.
Okay, first things first. We have to do a super quick review of the 3 fundamental laws that basically run the whole show. Let's do it. So what's the big takeaway here for your exam? It's this. If you read the words at rest or constant velocity in a problem, bam, you immediately know the total net force is 0. No net force means 0 acceleration. It's a huge shortcut.
Now, this is the big one. Sigma F equals ma is literally the most important equation you're going to use. Think of it as the engine for everything. The sigma F part, well, that comes from the picture of forces you're about to learn how to draw. And the ma part is the motion you're solving for. This equation is the bridge that connects them.
And for the third law, just remember this one simple thing for your problems. These action-reaction forces, they always act on different objects. Your book pushes on the table pushes on your book. You can't just have a force hanging out all by itself. It's always a pair.
Okay, let's get to the master key. I'm not kidding. If you can nail this one technique, you are golden. We are talking about the free body diagram.
And listen, this is absolutely not an optional step. It's your blueprint. It's how you take a bunch of confusing words in a problem and turn them into a picture that you can actually solve. You get the diagram right, and believe me, the math just falls into place.
So, how do you actually draw one? Just follow these 4 steps every single time. It'll save you from so many headaches. First, you isolate your object. Then, draw it as a simple dot. Easy. Third, you draw all the force arrows acting on it. And the last step, which is super important. If you have any forces at an angle, you've got to break them down into their x and y pieces.
Okay, enough talk. Let's actually put this thing to use. We're going to tackle a classic problem, one you are almost guaranteed to see on your exam, a block on a frictionless inclined plane.
Why is this one so common? Well, because it's the perfect test of whether you can handle forces that aren't just straight up and down or left and right. It makes you use the system.
Okay, let's draw our diagram. First force, gravity. That's the easy one. It always points straight down. Now the second one is the normal force, and this is where so many people mess up. Normal in physics just means perpendicular. So the force isn't pointing straight up, it's pointing perpendicular, straight out from the surface of the ramp. Get that right. And here is where the magic happens. That gravity vector is at a weird angle, right? We can't work with that, so we break it down into 2 component vectors. One part of gravity is perpendicular to the ramp, and it gets completely canceled out by the normal force. But that other part, the part that's parallel to the ramp, that's the one that's left over, and that's the force that makes the block actually slide.
And look at that, the payoff. The net force, the only one making it move, is just that parallel bit of gravity, mg sine theta. So you plug that into our big equation, sigma F equals ma, the m on both sides cancels out, and boom! Your acceleration is just g times the sine of the angle. So clean.
All right, that was the nice, clean, perfect world version. But you and I both know that exams and the real world, they have friction. So let's level up and add it into the mix.
Okay, so with friction, the key is knowing which one you're dealing with. You've got static friction, that's the stubborn one. It's what keeps something from starting to move. Then you've got kinetic friction, which is the force that slows something down once it's already sliding.
And you know what? Adding friction to your diagram is actually really simple. Don't let it intimidate you. It's just one more arrow. It always, always, always fights against the motion. So you just figure out which way the object is sliding, draw the friction arrow pointing the other way, and add it to your sigma F equals ma equation. The process is exactly the same.
Okay, let's bring this all together. I want to give you one final, crystal clear strategy to take with you into that exam room.
This right here. This is your 4-step plan for every single problem. Memorize it. Burn it into your brain. 1, read. 2, draw the free body diagram. Do not skip this. 3, write your sigma F equals ma equations for your x and y directions. And 4, solve for whatever they're asking for. That's the game plan.
I mean, this quote just says it all, doesn't it? The free body diagram is the bridge. It connects the word problem to the math equations. You have to build that bridge first.
If you can master the diagram, you've pretty much mastered the entire topic.
So, if your brain is fried from studying and you can only remember one thing from all of this, what should it be?
It's this. This is your mantra. See the problem. Draw the diagram. Write the equations. Solve. Don't get freaked out by long word problems. Just follow the steps. You're translating the problem from English into the language of physics. You have a plan. You've got this. Good luck.